So let's do a few more of these. So here's a new recurrence relation. So here's t of n equals 2 times t of n over 2, all right? With no overhead. Okay, so in this one, the way you want to think about this is that every time I recurse, I take my input, I split it in half, and then I go recurse on both halves, right? So unlike with binary search where I would only recurse on one half, with this one I'm recursing on both halves. Okay, so and the way to think about this is this is essentially equal to t of n over 2 plus t of n over 2. So with this one, I'll give a basic, a base case like this where t of 1 equals c again, but here there's essentially no recursion overhead, right? I don't have a plus c or plus c1 up on the recursive part of this. So let's chase this, right? This is going to be kind of similar to the other ones we've seen, so it's not going to take too much additional effort to get this thing worked out. So I'll write my recurrence relation here. I'll give myself my space, and then I'll write my generic expression, my utility expression over here on the right. So this is equal to 2 times t of x over 2. Okay, so here's what we're going to do. We're going to find an expression for t of n over 2 and then plug it back in. Same program as always, right? This should hopefully be getting boring, right? If I'm doing my job, this shouldn't be new, right? This approach should be something that you see coming. So what do I say? I say let's let x equal n over 2 and then solve it. So t of n over 2 equals 2 times t of n over 4. Okay, so what's this mean? This piece here means that if I give this algorithm an input of size n over 2, then it'll recurse twice, and so it'll cut it in half into pieces of size n over 4 and recurse on both of those. Okay, so let me substitute this back in, and I get 2 times, and now let me be careful with my bookkeeping, 2, which comes from above, times 2 of times t of n over 4. Okay, so here's where the bookkeeping really matters, right? If you mess this one up, it's going to lead you up into all kinds of dangerous places. But essentially what we've got is there's my 2t of n over 4. That goes here. Okay, and then I can simplify. And those 4's combine, and I end up with 4t of n over 4. All right, I'll do one more step. I let x equal n over 4. Right, line there. And this gives me t of n over 4 equals 2 t of n over 8. Right, what does that mean? It means if I give this thing an input of size n over 4, it splits it in half. And what it gets is inputs of size n over 8, and then goes and recurses on both. Right, so the both is that 2. The n over 8 shows up in the argument. And then I substitute that back in. I'm going to be careful with my bookkeeping. So here I've got 4 times 2 t of n over 8. And this equals, the 4 times 2 is 8. This equals 8 t of n over 8. Okay, the pattern is clear, right? Let's look at that one, and that one. And what I have is, the factor out front is increasing in powers of 2. The factor on the argument is decreasing by factors of 2. So I have the following pattern: 2 to the k times t of n over 2 to the k. Okay, how do I anchor this? Well, I bring back my initial condition, or my base case, and I say t of 1 equals c. So let me try to solve n over 2 to the k equals 1, right? So that I figure out how many times I have to recurse to get down to that input size. And this gives me what we've seen so many times already, n equals 2 to the k. So anytime I see 2 to the k on the left side, I can just replace that with, apologies for that, that was a disaster. So let me make sure that this is all saved. Here we are. Okay, good. Oops, full screen. There we go. Good. So what does this tell me? Anytime I see 2 to the k on the other side, On the left side, I can just replace that with n, right? So let me just make sure that this is written as it should be, n equals 2 to the k. Okay, so now what I can do is substitute this back in over here. So 2 to the k is the same thing as n. That's what I just wrote there above. So I can replace that 2 to the k by n times t of n over n. And what is this? It's n times t of 1, which is equal to n times c. So in the end, what I have is t of n equals n times c. Okay, which means that this is a big theta of n algorithm. Right, so this is a linear time algorithm. And if you think about what we were talking about, this kind of makes sense. So suppose I give you an array, and I say the way your algorithm works is every time it recurses, it's going to find a split point, and then it's going to go recurse on this piece, and it's going to go recurse on this piece. Nothing is ever thrown away, right? And so as it recurses, it's just going to keep dividing the array into smaller and smaller pieces. And eventually it's just going to be a bunch of one-element arrays. It'll process them and pass them back up. So the input is never growing smaller, but we're also not overlapping any work. Okay, so it kind of makes sense that we'd end up with a linear runtime with this algorithm. All right, so let's stop this one here, and then I'll go and do one more where I add one more level of complexity before we wrap these up.